One of my favorite moments in any project is exploring a brand new idea on paper for the first time. This is a snapshot of my research notebook, describing a new idea I had several years ago. I love the excitement of writing down the equations for the first time and seeing whether or not the math supports the idea. In this case, the idea was to take two tubes, which are the right size for one to nest inside the other, and cut a pattern of slots in their sidewalls. The slot pattern leaves some material intact on one side to create asymmetry in the stiffness of the tube. And this is the key aspect behind how the device will work. We can put one tube inside the other and rotate them so that the stiffer, uncut regions are opposite one another, 180 degrees apart. Then we join the tips together. Depending on the material, which could be metal or plastic, this could be done by a variety of methods, such as welding or glue or epoxy. We can then pull or push the inner tube in and out of the outer tube. This causes the device to bend because of the asymmetric stiffness that we designed into the tube cut patterns. By controlling the push-pull motion and the rotation of the tubes, either manually or robotically, we can then steer the device and reach many locations in space. A potential application of this concept is to steer surgical tools at the end of flexible endoscopes. This diagram shows an end-on view of a typical endoscope with camera and channel for passing tools to the end. Typically, the tools cannot be controlled beyond insertion and retraction, but our thin-walled steerable sheath idea can fit in the channel and still carry tools inside. So how do we make these concept drawings an actual device? Well, we started by 3D printing in the lab to make rough prototypes. A single device can be made in under an hour, which then allows us to evaluate lots and lots of possible designs. These prototypes show that a variety of shapes and motions are possible by simply changing the parameters of the cut pattern. We performed experimental tests on these prototypes to see if our mathematical models from the first slide correctly predicted how they would bend and move. Since the experiments agree with the model, we can now use this model to design a steerable device to achieve any desired set of curves in space that we want. We also expanded our lab's manufacturing capabilities by learning how to precisely cut very small tubes with a laser. These tubes are about 2 millimeters in diameter, and we can make clean cuts into their walls as thin as a human hair. It took a while to create our cutting system, but we can now reliably produce these designs for testing. On these new metal prototypes, we characterized the mechanical strength so that we know the device will be able to exert enough force when it needs to. We explored additional cut patterns for custom shapes, and we got an endoscope system to test how well the sheath can be deployed and controlled through it. We also made a robotically controlled version with 4 tubes that form 2 independently controllable sections. This allows the robot to reach even more points in space and more curves as the motors translate and rotate each of the 4 tubes at the base. The robot's motion can be directly commanded through a user interface. Doctors and patients really need more controllable instruments in many applications, but it's a long journey from the research lab to an actual medical product. There are all kinds of challenges: building a value proposition, working within the clinical workflow, regulatory hurdles, volume production, marketing, and this is more than a humble research lab can do by itself. So I reached out to some folks with actual experience commercializing medical robots. We created a new startup company called Endothea. This is led by entrepreneur Bob Webster and physician Duke Harrell at Vanderbilt University, who are previous collaborators of mine. And business development is led by Scott Webster. Josh Gafford leads the product development with Patrick Anderson. The first thing we did is to identify the best application for our first product. Treatment of kidney stones is a widespread medical need. A thin endoscope travels to the kidney and can blast the stone into small pieces with a laser and remove them with a small wire basket. However, urologists often struggle to treat large stones in challenging locations. This is because baskets and lasers can only go in and out of the endoscope. In this endoscope view, the stone is in the upper right-hand corner. The basket tool is unable to reach and grab the stone because it can only move straight, and the scope cannot steer further because it is stuck against a wall. If we only had a controllable sheath that could steer the basket up and to the right, and that's exactly what our device will provide. When the endoscope cannot aim with enough control, our steerable sheath will take over and direct the laser or the basket towards the stone to treat it. Even at this tiny scale, there's enough room for our thin-walled sheath inside the endoscope to carry a laser or basket tool for stone treatment. We developed an ergonomic handle to enable the urologist to control the steerable tool. The handle is designed to mate to a standard urology endoscope so that the physician can control both the scope and the steerable tool simultaneously. The system uses a flexible transmission to deploy tools down the endoscope. This is what it looks like inside. You can see there's a simple lever mechanism that provides control of the tube translations, which then steers the tool at the tip. Lasers or baskets can be inserted down through a feeder tube, and the entire handle couples to the endoscope with a ball joint that allows the handle to be repositioned for ease of use. Here's an example prototype that shows the scale. This is a real endoscope that's 3 millimeters in diameter. Our steerable aiming tip is about 1 millimeter in diameter and allows the laser or basket to be passed through it. We built this simulated kidney environment to test the functionality of the system in a benchtop lab setting. This video shows the operational device. On the right, you can see how quickly the stone is broken up when the laser is steerable, compared to the slow process using only the scope on the left. Similarly, grasping a stone with the steerable aiming tip is so much easier and can reduce procedure time versus using a standard non-steerable tip. So the journey of this research idea is really just beginning. Beyond Endothia's initial efforts to improve kidney stone treatment, we want to push the capabilities of the technology further to eventually improve more complex procedures like cancer removal and hopefully save lives. You never know where the ideas will take you next.